All right, so today we're going to get into topic 14, which is hypothesis testing. And today we're going to focus a little bit more on t-tests. But before we get into material, first I want to congratulate all of y'all for officially completing phase one. Everyone passed phase one in this cohort, so congratulations and really good work. Next, if you saw in the Slack channel yesterday, Amber posted a link to an end of phase survey. So please fill that out if you can. No, please fill that out, not if you can. Fill that out, definitely. The feedback helps me, helps this entire program. And I won't see your feedback, rather it gets kind of relayed to me. So feel free to write whatever you want candidly. See what else. Okay, if you haven't yet, please put your stand-ups in the thread. Again, I will call you out if you don't put your stand-up for the week. So please just put your stand-ups in the thread. Talk about what you did over the weekend or last week. Talk about what your goals are for this week, and then any blockers. That's just really important. A really important habit to get used to, because most tech companies especially do enforce almost daily stand-ups. So good to get into that habit. Let's see. One other thing I wanted to remind you of, right after this session at 3 p.m. Eastern, there's actually going to be a Q&A. And this Q&A will be with two former data science students of Flatiron School. Unfortunately, this won't be recorded, just so people, I think, feel more comfortable asking questions and participating. So this won't be recorded. So if you have the time, I do recommend going to that Q&A session. It will be pretty open. I think, yeah, they'll be pretty open to questions. And that's happening right after this study group. So please go if you can. The Zoom link is on our homeroom page. Any questions or thoughts on anything I just mentioned? Okay. Reminder, tomorrow I'll be giving out your project pairs, so look out for that. And tomorrow as well, I will be talking about what kind of data to look out for, because our project specifically, we haven't gotten to that material yet, but I want to give you all the chance to at least familiarize yourselves with, I guess, each other, and also the data set that you want to use. So I'll talk more about that tomorrow. But today, to start, I've been hearing a lot of panic, rightfully so, about the material that we've been going through so far. It's seemingly abstract, not immediately clear what or how we're going to be using the statistical material that we're learning. I 100% relate to that. It is very abstract right now. So what I'm going to do is I want to show you all an example of what we will be doing for our project. And hopefully this will give you all a better sense of how we're going to be using the stat stuff that we're covering like today and last week going forward. So we'll get back to the slideshow later. But this is just one of the labs that is in topic 19, I believe. And our project is going to heavily focus on topics 18 and 19, which we'll get to next week. So just to get the sense of what's going on, this is an example of a results table that you're going to get. The model that we're going to be going through is linear regression. And the whole idea of linear regression model is predicting something using other things as features. In this example that I have over here, this is actually the miles per gallon data set that we had talked about before. I think if I scroll up, I guess you don't really see it here, but you can see miles per gallon. We have acceleration, displacement, horsepower, weight. We sort of looked at this data set back in phase one, but this is that data set. And the idea here is this lab in particular, you're building a model to try and predict miles per gallon using all of these other features. And so all of this will actually be done automatically for you. However, where stats comes into play, and some things that maybe look familiar, here you can see standard error, T. So these are actually T statistics, P-values, and this is actually going to be particularly important, and then confidence intervals. A couple other things that we'll be talking about this coming week, actually, we'll be talking about the F statistic as well. And so this just goes to show, and of course, when we come to this, I'm going to explain what this means in this context. But a lot of this stat stuff that we're doing helps to give us a foundation for interpreting this information. So I know a lot of the stuff seems very, very abstract right now. If you all want to be statisticians, then yes, that stuff is even important. that stuff is going to be important, but for our purposes as data scientists, it's really a matter of fact of like, okay, you see here, this is a p-value of 0.519. What does that mean? And we will get to that next week. But just want to give you all like a sneak preview of how we're going to be using the material that we're going through now for data science applications next week. And hopefully this will maybe ease some of the panic that I've been hearing during these one-on-ones. Any thoughts or questions? All of this stuff, please don't worry about this right now. I'm going to go through all of this next week. So yeah, other than about this, any other questions? Okay, so just again, to reiterate, our job as data scientists is to look at these numbers and interpret what they mean. So therefore, it does help to understand, like, statistical testing processes, how to interpret p-values. But we never have to really calculate these things by hand. And I know a lot of the labs have you do that, but I really want to set the expectation that you're not going to be expected to code these from scratch ever. Okay, let's get into material for today. We're going to be talking about hypothesis testing, which is something that we started with last Friday. But today we're going to do a couple more tests. So let's take a look. We're going to review hypothesis testing. That statistical testing process is pretty important. We're going to talk about p-values. More specifically, we're going to throw out a definition of p-values that I think is going to be important to remember. We're going to talk very briefly about effect sizes. Effect sizes will come back again tomorrow. And then we're going to conduct a couple t-tests. And then we're going to end off with introducing type 1 and type 2 errors. So for today, there will be a couple loose ends that will get resolved tomorrow. Just want to set that expectation. Okay, so let's get into it. This is what we talked about last Friday, the statistical testing process. So first, there are our 3 steps of setup: setting up the hypotheses, picking your test, as well as picking your alpha. And then you have your calculation phase of like calculating your test statistic, your p-value, and then finally your interpretation. Again, from what we saw earlier, the interpretation step is really what we have to focus more on. So we'll talk about that. Okay, p-values. A good definition to remember for p-values. A p-value is the probability of observing a test statistic at least as large as the one observed by random chance, assuming that the null hypothesis is true. So if you remember our IQ test example from last time, and I'll explain this again in this upcoming context, but if you remember our IQ test from last time, the population had an IQ of 100, and then this sample that had gone through tutoring had an IQ of 103. It got a p-value of, I want to say, about 8%. And a p-value of 8% means that there's an 8% probability that that observed 103 IQ just happened by random chance. It just so happened that our sample was already maybe had a little bit of a higher IQ to begin with. So ideally, if we want to observe an actual effect, we want the p-value to be very, very small or as low as possible, because then that effect didn't just occur by random chance. So that's, I think, to be honest, when I was going through stats like throughout college, this was a concept that was kind of difficult for me to grasp. But I think through examples, hopefully it'll be a little easier to understand. And if anyone has any questions, you can just let me know. Okay, so that's p-values. Next, effect size, which is again something we're going to talk about more tomorrow and on Thursday. Effect size is basically a statistical measure of the difference between two groups. This will come into more, we'll see this in action more so tomorrow and Thursday, but we will have kind of one example later, kind of. So effect size measures the difference between two groups. A standardized form of effect size, like how you remember we had like z-scores for standardized values. A standardized effect size is actually known as Cohen's d, and it is taken by the effect size divided by the standard deviation. Formula, again, not that important for now. We'll see some examples of application later this week. And basically it measures the difference between groups in terms of the number of standard deviations. Now, just some good numbers to remember, I guess not even to remember, but to be aware of. Cohen's d is measured between 0 and 1. And these are sort of the commonly used thresholds for what's considered a small, medium, and large effect size. This is merely just like contextual knowledge, good to know, and we'll see effect size more when we talk about statistical power tomorrow and also the day after. Okay, let's get into some t-tests because that's going to be the bulk of what I want you all to take away from today. Okay, so on Friday, we talked about one sample z-test, which was, we were measuring whether tutoring had an effect on this like group of students and their IQ. So the setup is going to be very similar. So let's take a look at this setup. Acme wants to improve sales performance, and past sales data indicates that the average sale was $100 per transaction. After training the sales force, recent sales data from a random sample of 25 salesmen is shown below. So these are just our numbers. And the idea here is we want to see whether sales performance has improved based on this sample. So what is the main difference between a t-test and a z-test? And we'll get into this later as well. The main difference between a z-test and a t-test is that for the z-test, we knew our population standard deviation. And for our t-test, we do not. So as long as you are given the population's standard deviation, you can use a z-test. If you're not given population standard deviation, which actually surprisingly, a lot of times, well, not surprisingly, but a lot of times you actually don't have the population standard deviation. If you don't have population standard deviation, straight away, you use a t-test. Quick segue, again, if you want a reminder of all of the conditions for all of the tests, it is down here. I put the statistical test summary down here. And you can take a look. It should bring you to a Google Drive folder, which has statistical test summary. We're actually going to go through all of these tests. And if we zoom in, you can see here, it's going to be blurry, but basically here it says one sample z-test, one sample t-test, and you know the population standard deviation and you don't know the population standard deviation. So we're actually going to get through all of these tests by the end of the week. So yeah. This is a place where you can just see all the summaries of everything. Oh, another plus point here is that you have the Python line for running all of these tests in, through stats models or through SciPy. So yeah, that is there, just for your reference. Okay, back to this. So we have this sample data, and the idea here is we want to take a look at this sample data and figure out through this sample of 25 salesmen, is there an improvement or a statistically significant improvement in sales where the average in the past was about $100? So let's go through our statistical testing process. So first we set up our hypotheses, and this is a one-tailed test, and it's a one-tailed test because we care about whether sales performance improves or not. Again, to reiterate, if you want to know whether it's a one or a two-tailed test, you have to pay attention to the setup of the question. If instead of improve, they use the word like wants to see if sales performance changes or there is a difference in sales performance, and that is actually an indication of two-tailed test because they don't specify the direction of change. But in this case, it's pretty clear because they're talking about improvement. It is a one-tailed test. So therefore, it is strictly greater than 100. Okay, here we just set our alpha at 0.05. And we know because this is what we're learning, we're conducting a one sample t-test. All right, some numbers to note and calculate. We have our population mean, mu, which is 100 because this is something that they gave us. The average sale was $100 per transaction. The number of points in our sample. Number of points in our sample is 25. And these two, X bar and S, which is standard error, these were both calculated based on these numbers that were given here. So these two numbers are given here. And DF, which stands for degrees of freedom, not data frame. But if you remember at the end of last Friday's session, we talked about when you're doing some sort of t-test, degrees of freedom is important to know because, well, it's just important to know for t distribution, but basically degrees of freedom for a one sample t-test is always number of points in your sample minus 1. So degrees of freedom here is 24. So these are numbers to note / I guess calculate. In this case, we were given an array, so we got these numbers from there. So this is our setup of our one sample t-test so far. Any questions about this setup? Okay, all right. So let's do some calculation and interpret. There's a lot on this slide, but bear with me. The calculation for t-statistic is this, which is fine, good to know. Also, if you refer back to this over here, you can see that it is a very, very straightforward t-test. You give it your, A is basically your array of your sample data. The population mean, you can just give it 100, and that will do it for you. So I'm not going to go into the calculation too much, but this is the formula for a t-statistic. Also, there is a t-table, which I thought I hyperlinked here. I think I hyperlink it here. Okay. So there's our t-table, and I'm going to have us look through the t-table in a little bit. But basically, same idea as last time. You can sort of think of it as this is technically the t-distribution with 24 degrees of freedom, but it works very similarly to how we were using our normal distribution curve the last time. So using our t-table, we can actually look up critical t-values. So in this scenario, we have a one-tailed test, and we have our alpha set at 0.05, which is over here. So we know we want to look down this column. And then you can see here on this axis, we look at the, so many ads. So we look at the degrees of freedom, which in our question, oh my God, in our question, we were looking at 24 degrees of freedom. So which column were we at? Here, over here. If we look down 24 degrees of freedom, our critical t-value is 1.711. So for a t-test, the t-table works slightly differently from our z-table because this gives us our critical t-value. If you remember from Friday, which I don't expect you to, our z-table gave us different information. Our z-table gave us the associated p-value with a z-score, so kind of different. But here in this case, we are given the critical t-value at different critical values, at different values of alpha. So no matter what your alpha is, you can look it up and then figure out what your critical t-value is. And we'll look at this 1.711 on our slide. Okay, so basically, the critical t-value is 1.711, which is this green dotted line over here. Our sample t-statistic was 3.5781, which is actually out here. So remember, we're looking for a difference or an increase in our sample. So the further away from the center of our curve here, the better. Just intuitively, the further away, the better. So just by looking at this diagram and also comparing these two t-values, we can reject the null hypothesis and say that, yes, the sales did improve statistically significantly for that group of salesmen. Any questions about this? Okay, on a similar note, I don't have that here, but if you were to plug into this formula here, which I know it's blurry, but if you were to use SciPy to calculate or run this one sample t-test, it will actually give you both the t-statistic and the p-value. So because they give you a p-value, and this will probably give you like a very small p-value. I'm guessing like less than 1. Sorry, less than 0.01 even. But given this p-value, you can just compare whatever the p-value is to your alpha. And as long as your p-value is smaller than your alpha, you can reject the null hypothesis. So as long as your p-value is less than 0.05, which is kind of like the allowance that you give for something to randomly occur or occur by chance, based on our definition of the p-value that we had earlier on, you can also look at it that way. So similar as what we were doing on Friday, 2 ways to figure out the conclusion of a test. You can either compare your statistics, your t-statistic in this case, or compare your p-value to your critical, to your alpha. Does that make sense? Any question? Right, so based on this value given here, you can basically conclude that sales performance has improved as a result of, training, as a result of training. Okay, so that was our one sample t-test. We're gonna move on to a 2-sample t-test, which tests slightly different things. So far, with both our one sample Z and t-test, the setup was very similar. We want to see how different is one group of data points to the population. Now, in a two-sample t-test, you're actually comparing two groups to each other. So it is used to measure if two population means are equal. So let's set up this experiment for our two-sample t-test. So in the context of controlled experiments, you often see talk about control group and experimental or treatment group. So in a drug test example, which we're going to go through in a little bit, the control group is the group that's given the placebo, and treatment group is given the actual drug. So you can sort of see, I mean, if you're doing like, I don't know, clinical trials are kind of conducted like this as well. I mean, this is oversimplified, but kind of similar. A group is given like a dummy drug and a group is given the actual drug, and you want to see that there is a difference in the change of whatever they're measuring based on this drug to see whether the drug is effective or not. So researchers here in this case are interested in the average difference in blood pressure levels between treatment and control groups. So here, the 50 subjects in the control group have an average systolic blood pressure of 1 to 1.38, and they've been given the placebo drug. So then 50 subjects in the experimental or treatment group have an average systolic blood pressure of 111.56 after treatment with the drug being tested. So cool. We can see that we have two groups. Each group has 50 participants. And within the two groups, there is an absolute difference in their average values. So there's about a difference of negative 9.82. So basically through this drug, based on the averages of the two groups, average blood pressure went down by 9.82. Now, with 50 subjects in each group, how confident can a researcher be that this measured difference is real? Basically, to evaluate this, whether this 9.82 difference is statistically significant, you're going to do a two-sample t-test to see if that difference is significant enough based on all of these parameters or not. Questions about the setup before we move on? Okay, we're going to go through a very, very similar process as before. First, we're going to set up our hypotheses. So hypotheses for a two-sample test. And remember, two-sample test is different from two-tailed. So there's one sample, two-sample. There's also one-tailed, two-tailed. Those are two different things. One sample versus two-sample is basically, are you comparing one group to a population? That's one sample. Are you comparing one group to another group? That's a two-sample. That's sample. One versus two-tailed depends on the hypothesis here. If we are measuring whether there is an increase or decrease in blood pressure, that makes it a one-tailed test. So our hypotheses, instead of having this not equal to sign, would have a strictly greater than or lesser than sign. So that's one-tailed or two-tailed. In this case, we're actually doing a two-tailed test because here, as I mentioned before, they talk about measured difference. They don't really talk about whether their blood pressure should go down or up. There's not really language of that. So here you can see average difference in the blood pressure levels because they use specifically the word difference, and syntax, or is it syntax or what's the word? Terminology is kind of important with statistics, especially if you're like doing intense stats. And if you're a statistician, that becomes way more important. But in this case, because they use difference, not improvement or improvement, we're doing a two-tailed test and a two-sample test. So hopefully that did not confuse you all more, but just know that one two-tailed is different from one two-sample, because I know some people have been confused about that in the past. Okay, so this is our hypotheses, and there are two different ways that you can write this. This is one of the ways, which I think is more standard, but I have seen even in stats textbooks, this has been slightly different. So I'm actually going to write it down the other way that you can do it. Here, the null hypothesis of mu1 minus mu2 is equal to 0 is just saying that the two mu's are equal, right? If there is a difference of 0, basically means they're equal. Another way that it is somewhat commonly written as well, just in case you come across it, is, oops. Oh, that's not nice. Okay, it's just simply mu1 equal to mu2. That's another way to write it. So that's equivalent. These are equivalent. And then the alternate hypothesis that it's not equal to 0. If it was a one or two tilt test, if it was a one tilt test where you were measuring it like an increase or a decrease, then of course you can have your strictly larger than or strictly less than 0. Or you could have mu1 not equal to mu2. And if you were testing for a specific direction of difference, then you could have it as mu1 greater than mu2, or so on and so forth. So in this case, because the question, the setup asks for a difference, we're using this version. If they ask for an improvement in blood pressure, and improvement means the blood pressure goes down, we would use this version because we want mu2 to be less. But in this case, we're not doing that. But just in case, if the question was phrased very slightly differently, just know that you would have to switch it from a two-tailed test to a one-tailed test. Okay. Another thing to talk about is the alpha here. So alpha is 0.05, but when you have alpha for a two-tailed test, it's actually slightly different because you actually are splitting your 0.05 critical values across two sides. So whereas previously, and let me see if we can go back to this. Previously in this example, this shaded area in this one-tailed test with an alpha of 0.05, this shaded area is 0.05. If it's a two-tailed test, each shaded area on each side is 0.025. So you're actually going to take each of these and they're going to share the 0.05. So the area under here is actually 0.025 and similar to the area here. They add up to 0.05. But because we're not sure at this point whether it's going to be an increase or a decrease, we test for both. Okay, so we're splitting our critical values across both sides. And the critical value is symmetrical. So whatever we look up in the t table later is going to be plus minus the same value. Okay, so some numbers to note and calculate. Both samples have 50 people, and these were the mean values that we got from the question earlier. The control group had a systolic blood pressure of 1 to 1.38, and the treatment group has the blood pressure of 111.56. This is a bunch of formulas that calculate the t-statistic because it is a little bit more complex to calculate a t-statistic for a two-sample test. I know in the labs they actually have you code this out manually. I personally don't think it's very important to know how to do that. Maybe for the purpose of practicing your Python, but it's not important to memorize these formulas at all. But basically, you end up with a two-sample t-statistic of negative 1.891. And the t-statistic is negative because we've seen a decrease. So this is, I guess, the calculation phase. Any questions at this point? Okay. So we have that two-sample t-statistic of negative 1.891. We know we need to compare this to critical t-values. So how do we find this? We go to our t-table. Oops, let me clear this. We go to our t-table, and then we look for two tails of 0.05. So that would be this column. And you can see technically one-tailed is equivalent to like the one-tail value is always half of the two-tailed value. So we will look this up. And then we go degrees of freedom. And in a two-tailed test, the degrees of freedom is actually 50 minus 1 plus 50 minus 1. So it's actually 98. Yeah, degrees of freedom is 98. Or is it 49? I think it might be 49. I honestly cannot remember. I think it's 49. Okay, sorry. Whatever it is, you can look it up, but I know whichever one, it will give you the same result. But basically, if you look down here, and if you remember, the more degrees of freedom there are, the more it starts to resemble a normal distribution. So therefore, as the degrees of freedom rise, you don't need to get as granular with the numbers. So here you can see that after 30, it starts to increment, I guess, exponentially. So it goes from 40, 60, 80, 100. So you can estimate from there. Yeah. So based on this, I'm pretty sure that the degrees of freedom should be 50 minus 1, which is 49. So apologies about that. So basically, because 49 lies between 40 and 60, these numbers are also pretty close together unless you get a t-statistic of like, 2.01, that's like just right between these two values, then sure, I will tell you that doing it in Python will give you very, very specific values, or very, very, what's the word? They'll give you a lot of decimal places so you can see exactly where that number lies. But in this case, we know that our t-statistic is about 2. Our critical t-value is about 2. So let's take a look at what that looks like graphically, because I do think that that's easier. All right. So because our t-statistic is about 2, on each side, our critical t-values are going to be 2, roughly positive 2, negative 2. Now that t-statistic that we got earlier was negative 1.8, which actually lies within the critical values. So you see, if this red line was outside either of the dotted lines, then yeah, we can reject the null hypothesis. But because it was within these lines, it's not different enough to have a statistically significant effect. So the conclusion here is we fail to reject the null hypothesis, and the drug actually does not make a difference in the blood pressure levels. So earlier we saw that yes, we had a negative 9.82 difference in the blood pressure levels, but statistically not significant enough to confirm a difference. So that's how you do that. Or even easier, if you just run this line here and experimental and control here, I can tell you that these are each arrays of these numbers. I think this is actually from one of your labs. So these are each arrays. And then when you just run this one line, they give you two things. They give you the t-statistic right off the bat, and they also give you the p-value. So just by looking at the p-value here, we know that since it is above 0.5 or even above 0.25, this is just saying that the area under, let me draw this. The area under here, so like the left side all the way onto the red line, this area is 0.06 or 6%. So that means there's a 6% chance that this is random, which does not meet our threshold requirement of 0.05. Of 0.05. So therefore, if we do this Pythonically, like in Python, just based on this p-value, we immediately can say that, you know, this drug does not have an effect. So that's how much easier it is via Python versus doing all of that calculation. All right, any questions at this point? Okay, so next we're going to talk about, I think, type 1, type 2 errors. Let's see what's next. Okay, yeah, type 1 and type 2 errors. So there's different perspectives that we use type 1 and type 2 errors for. The two perspectives that we're mainly going to use them for is first in evaluating results. If you have false positives, false negatives, we can look at type 1, type 2 errors like that. Or we can look at them from a statistical testing process level, which is basically the probability of making false positives and probability of making false negatives. I have to say this because in phase 2, we're going to be using it this way, which I'm about to explain. And then when we get to phase 3, it's going to be slightly different. So I'm just going to make that, I'm just going to say that for now. So in statistical testing, everything is based on a probability or statistical significance, right? Even though we had a 9.82 difference in our two groups, there was basically our conclusion was that there's a 6% chance that this group had already like a naturally lower blood pressure, for example. So there's a 6% chance that that just happened completely by chance. So everything is based on a probability. So there are situations where we will reject the null hypothesis when we shouldn't have, and vice versa. So for example, we had a 6% chance that that was random. However, because that's really just a probability, what if the drug actually did work, but I guess not well enough for us to pass that test, right? And in that case, we should have rejected our null hypothesis, but we didn't. So this is the opposite. We type 1 error. So what we might have done a type 2 error, which is basically not rejecting the null hypothesis when we should have. But there's also type 1 error. So we'll talk about type 1 errors first, and then tomorrow we're going to talk more about type 2 errors. Type 1 error is basically the situation where you reject the null hypothesis when you shouldn't have. And type 1 error is actually pretty easy to calculate and figure out. your type 1 error or probability of your type 1 error is equivalent to your alpha. It's equivalent to whatever critical alpha you set. And the reason for that is before you even conduct your test, before you even start conducting your test at all, if you have an alpha set at 0.05, for example, in just A1 tilde test, this will be our critical value. No matter what we do, and this is, again, before we even conduct our test and calculate our statistic, there is a 5% chance that we reject our null hypothesis based on the fact that we don't know anything about our sample yet. There's a 5% chance that we reject the null hypothesis. And the idea here is that, yes, something might fall into here, but based on the definition of p-values, that could have happened by random chance. So it's kind of a few things at play at the same time together. So just know that the probability of a type 1 error is equivalent to your alpha. Does that make sense? Okay, that's kind of like a definition to remember. A more common definition used, though, is rejecting the null hypothesis when you shouldn't have. Usually when people ask, what's a type 1 error, what's a type 2 error, usually they talk about that. Okay. The next slide, which is my last slide, actually. Let me go back to the mouse. Okay. Is type 2 error, which we will get into more detail tomorrow, and then also in practice on Thursday. So a type 2 error is failing to reject the null hypothesis when it is actually false. So basically false negatives. So the probability of type 2 error, there's actually a Greek letter for it. It's beta. And it is connected to this other concept that we will get more into tomorrow called the power of the test, which is 1 minus beta. So I'm not going to get into calculation now because here you can see that there are 2 bell curves and we haven't really gotten to that yet because we will get to that tomorrow. Basically, what I want y'all to think about is in any situation, sometimes you prefer a type 1 error over a type 2 error, and it's typically a trade-off. There are situations where you rather make false positives. There are situations where you rather make false negatives. And this is something that will not just be constrained to statistics. This is actually something that we will think about with our machine learning models as well. So it's important to kind of think about that. And based on your phase 1 projects, I'm pretty confident that you are all able to think in context. So this is something that I want you all to continue. Some scenarios to think about. Let's say you have a COVID test, right? For a COVID test, would you rather have false positives or false negatives? And again, depending on what perspective you're coming from, it might be different, right? I think for most people, for a COVID test, you would rather have a false positive to be safe versus having a false negative and like you actually have COVID, but you don't, and you're just going out into the world and I don't know, spreading disease. So that's a situation where you would rather have a false positive than a false negative. To contrast that, there's also, let's say, spam filters. Is something spam or not spam? Would you rather have an email marked as spam when it's actually super important and shouldn't have been? Or would you just rather have, random messages once in a while that were spam but didn't get properly classified as spam? Depending on what you call positive or negative, it might be different. But do think about how in some situations, when you're making incorrect classifications, what would you prefer? That's actually something that I'm going to have you all think about, not for this project, but for the next one. But for stats, it's also pretty important to know that concept of like, there are going to be incorrect conclusions being made sometimes. And it's important to know what the probabilities associated with those incorrect classifications are, or these incorrect conclusions are. All right, so this is the last slide. Some of the loose ends that we will get to tomorrow include talking about power. And also we'll go back and talk about effect size some more. Effect size, which is back here. We're going to talk about power and effect size because these two are actually pretty closely related. So we'll talk about these two. So that's coming tomorrow. Also coming tomorrow, your project pairs. So look out for that. I'll be pairing you all up, similar to what we did for phase 1. Also, we're going to get into coding again on Thursday. So that's exciting. We're going to be coding. We're going to go through some actual examples of setting up and thinking about the formulating of statistical tests. through Python. And then we're going to basically conduct some A/B tests as well. And then, yeah, that's what's coming up this week. Any thoughts or questions at this moment? All right. Don't forget to leave your stand up if you haven't already. I will call you out if you don't. And then also, if you can make it in about 18 minutes, there's going to be a Q&A, that alumni Q&A. The link is on our homeroom calendar. So go to that if you can. It's not going to be recorded, unfortunately. So yeah, if you can make it, even just to like listen and absorb. Those are two fairly recent graduates, and they just started their new jobs, and they're both doing, I believe, pretty different things. So I think it would be good to just like listen and see what they're up to and what could be in store for you after graduation. All right, final call for questions. Going once, going twice. All right, if there's nothing else, I will see you all tomorrow back here, same time. Have a good rest of your day, everybody. I'll talk to y'all soon. Bye.